So, the challenge with that system we were looking at here is that while it does the job of bringing the output voltage to the right level, it really does not allow us to regulate the current. The initial current can go to 6 amperes, and that is not safe for the battery. It will not go to 6 amperes because something in the active circuit will anyway limit that current, but it is unregulated. We have no control over what that current is. So, what we will do is look at, okay, maybe we can make a minor adjustment to this system that allows us to regulate the current. So, we will say, okay, I still want a non-inverting amplifier. What I am going to do at the output is make this control a set of current sources. So, something of this sort, and these current sources is going to drive my output. So, we still have the same resistive divider arrangement. So, now the output voltage will eventually go to the same level, which is 1 volt into 4.2, which is 4.2 volt, no change there. The reason I have put these switches for the current source is because if you recall, we have two types of charging modes. We have what is called the preconditioning or the pre-charge mode, which is usually much lower current than the fast charge mode, and in that fast charge mode we will turn on all these switches. So, that is the reason those switches are there, but the big change we have made to this schematic is to add a current source at the output, which sort of says, you know, I can't give you more current than this is the most current you can give. So, if you drive me very hard, if the input difference is large enough that the amplifier starts to saturate, if the amplifier saturates, then you will get the rated current. Whatever is the current limit of this current source is the current you will get. You will not get more current than that. How that is done, we will not worry about. We will just understand that, okay, there is something in that circuit that will limit the amount of current. Okay. So, you would this is sort of the schematic that is typically used for a battery charger. Again, you know, when we talked about roles and responsibilities of an embedded system designer, one of the things is we are really not as embedded system designers going to be building the inner workings of the battery charger, right. We are trying to figure out which battery charger SoC to use, and in that context what we want is okay, first I want a working understanding of battery chargers, then I want to know how do I compare different battery chargers. I have 6 parameters that are of interest to me. Across those 6 parameters of interest, I want to compare different battery chargers, right. So, it is in that sense we are really not going to worry about, okay, what is the transistor implementation of the circuit. That is really not the intent of the conversation here. And for an if you plan to pursue a career as an analog design engineer where you are building analog chips, then 100% you need to go down that track. If you are pursuing a career as an embedded system engineer, then you can say that no, that is not the path I want. What I want to be able to do is compare different battery chargers and select the right one for my application. For that, what you need is a working knowledge of that, of the charging subsystem. So, this is where we will sort of leave it. We will say that, okay, the right implementation for the battery charging subsystem is to have an amplifier, and then that amplifier drives a current source, because the minute we put a current source at the output, we are limiting how much current it can give. Now, that current source is a current source bank because we have multiple modes where this current will need to be different. So, the pre-charge needs only 50 milliamp or needs only a fraction of the current. while the fast charge needs the full current, right. So, that is what we will that's how you would implement the charging subsystem. And now let us come back to the same questions, right. One of the things of interest is what is the charging profile, how will, again if I put a voltmeter and an ammeter right at the battery. So, let us say this is now going to connect to my battery, which we will show like a capacitor. So, this is our battery. Now, what I am interested in is plotting the voltage and current as a function of time. So, let us now try to do that. So, the first thing we will do before we do voltage or current is look at the type of charging or charging state, right. So, what happens is initially the battery will go through a phase that we call the pre-charge or the preconditioning phase. So, this is the pre-charge phase, pre-charge cycle, and then it goes through a state where it is charging to its maximum capacity. This charging phase is called the fast charge, and then it goes through this phase which is called the constant voltage charging, right. Now, let us try to plot the current. This is the current through the ammeter. So, how will that current look? Initially, I am going to, in the pre-charge, I am going to charge it with the nominal current. So, it is going to look like so. This I am going to call I pre-charge, right, and then the current is going to increase to this I am going to call as I fast, right. And once I go to the constant voltage case, at that point what is happening is the inputs are close to each other, amplifier is maybe not saturating. So, current will decrease with the RC time constant in an exponential manner. So, this current now, this current is going to do something like this, right. This will be an exponential decay, right. Now, that resistance etc., if it is limited by the battery resistance is also a function of the current that flows into it. So, these are not perfectly linear systems. So, it is very hard to say that is an RC time constant, but it will be exponential in nature. So, we are ignoring second order effects in this conversation, and for the purposes of this design it is perfectly okay to do so. So, this is how the current itself will look. How will the voltage look? Now, it is a capacitor. So, if you are charging with a current V Q is equal to I times T, or you can say that CV is I times T. So, C dV by dt will be I, or dV by dt is I by C. I by C determines the slope with which the voltage is going to increase, right. As long as the capacitor is constant and current is constant, the slope is going to stay constant. Now, pre-charge current is much less than fast charge current. So, I pre-charge is much less than I fast, which means that the slope in the pre-charge phase will be much lower, because slope is just I by C. So, let us say I had a certain initial voltage that the battery was at. Through this pre-charge phase, the voltage is going to increase with a low slope, right. And once it enters this fast charge, it is going to be charged with a higher current. So, it is going to increase, and it will still increase linearly. Okay, I am going to just redraw this slightly differently. It is going to increase with a much higher slope, right. And even let us say this is V bat rated. Once it enters the constant voltage phase, it will start to exponentially approach the rated voltage. So, this is what you will get, right. So, asymptotically it will go to V bat rated. So, the current through the battery will have a profile like I have shown in this green curve here. It will be I pre-charge in the pre-charge phase, and then it will jump to I fast in the fast charge phase, and then exponentially decay in the constant voltage phase. The voltage itself will rise with a low slope in the pre-charge phase because the current is small, and then once you go to the fast charge phase, current is much higher. So, the slope will the voltage will increase, and then once it enters the constant voltage phase, it is going to asymptotically go to the rated battery voltage, right. So, this is how the current and voltage will look for the battery charging, right. So, now let us now that we have these curves in front of us, let us now get into maybe component selection. So, now if I wanted to select a battery charger, right, I have many different SOCs I want to look at, many different battery charger SOCs I want to look at, and I am interested in thinking about, oh, okay, before I go compare all of these different SOCs, I know what all, I should first know what all parameters I should be looking for. So, let us try to list those parameters, or maybe before we get there, let us, I think one point I missed here, that let us just come back, revisit that point, and then go to keep moving forward. So, when does charging complete, right? What is, when does, in this we talked about the pre-charge phase, we talked about the fast charge phase. One of the things with this constant voltage phase is that when you look at this equation here, where V naught is equal to V in plus V bat minus V in into 1 minus T by RC. One of the points here is that V naught will become V bat only at T equal to infinity, right, until time approaches in, so it is asymptotically going towards V bat. So, at what point do I say, okay, now charging is done, right. So, I have to have a mechanism, because if I am going to wait for V bat, I will be waiting forever, I will never say charging is done. So, if I now have this charging profile, how do I now say, okay, charging is done, right. And charger ICs give you two ways to do it. One is to say that you can say, okay, the charging current is exponentially decreasing. What I am going to do is, I am going to come up with something that I call termination current. I will call this current as I term. Once the charging current goes below I term, once this exponential drop goes below I term, I am going to say charging is done, right. That is one solution, and is the most commonly used solution. Some other people will say, okay, you do that, on top of it you also have a timeout. So, you say that, okay, when you plug it in for charging, even if for some reason let us say this does not happen, right, that the current never comes to I term, and I am going to leave you to think about what might cause this charging current to never come to I term, but it is possible that happens. So, in that case you can say that, okay, after 10 hours, after 8 hours, you say charging is done, right. So, now let us come back to the point of chip selection, right. So, now when I want to compare different SOCs, what all should I look at, right. The first thing I should look at is I fast, right. I want to know how much is I fast, how do I set I fast, right. The second thing is, how do I set I term. Third thing is, how do I set I pre-charge. Are these under my control, or are these already set? Today this product I am using, right now I am using 1000 mAh battery, tomorrow I might use a different battery. So, how much flexibility do I have to go change something on the PCB, to be able to regulate this current, as this in my control. The fourth thing is, like I said, some of the points we talked about, right? Does it have short circuit protection? Or before we get to protection, let's talk about let's list the parameters of interest here. So I fast, I term, I pre-charge. Then I also want a charging done indication, right? So that if I have my microcontroller can say, oh, okay, this activity is closed, maybe I can go shut down the system now. Also, the as you are charging, you might have seen this in some devices, right? The color of that LED will change based on the current charging state. So if your battery is low, it might be blinking red, and it might blink vigorously. If as the charging increases, it might go to a breathing red, then it might transition to an amber, eventually to a blinking green, and then when the charging is done, to a stable green. If the MCU has to do all of this, then the MCU needs to know that know the charging state, right? The MCU is active through the rest of the charging cycles, so it knows, oh, okay, this is the color I should blink. But charging done, which is a decision, right? The rest is relatively continuous. So okay, I'm in fast charge, they are phases. Whereas charging done is a binary indicator, and that indicator is needed to hold that LED at full green. So the MCU will need that charging done indication, right? Then comes the other aspect, which is the aspect of safety that we talked about, where we need to know the battery temperature. So there is a charging done indication. We also need a battery temperature indication, right? So when we look at battery SOCs, we are going to look at them in the context of, do they provide all of these indications, right? So what we will do now is look at a battery SOC data sheet, and that's typically the activity you want to take up at this point, where you say, okay, now that I have the parameters of interest, let me now compare different SOCs. And how do you compare SOCs? You have to look at the documentation that they provide for that SOC, and that documentation primarily is the data sheet. So what you would do as a designer is to say, okay, let me look at each of these data sheets and let me see what the capability of that SOC is. So that is what we are going to do now for a battery charger SOC.